Okay, so here's roughly what we were talking about last time when we were talking about these various things we're going to think about in Chapter 6. A pretty vague discussion last time of, we're going to be interested in, vector line integrals and triple integrals and flux integrals, etc. And here's a bunch of arbitrary seeming conventions about what boundary means and orientations and these kinds of choices. So let me put it all together, roughly speaking, at least organize it a little bit for the moment. So here's what we have inside of R2. We have kind of a zero-dimensional collection of choices, one-dimensional, two-dimensional. Dimension referring to the domains that we're talking about. So on two-dimensional regions, for example, we're doing double integrals of functions, right? And then likewise on curves, we're doing vector line integrals of vector fields as the integrands, etc. Likewise on R3, in three-dimensional regions, right? We're doing triple integrals of functions, blah, 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 etc. Okay. All right, and we also have these operators defined at this point, the boundary operators. So if you give me a two-dimensional region in R2, we now have a precise orientation included notion of what it means to talk about the boundary of that region. Likewise for all these other boundary operators. Okay, so this is a starting point for some diagrams that we're going to create. We're going to kind of accumulate, sort of build up over the course of the rest of Chapter 6. By the way, there is a one-dimensional version. There's the R1 diagram. This is just, this is all Calc 1 sort of. If you have an interval, right, you can take the boundary of the interval. It consists of a couple of points, and we do integrals of functions. On those points, we evaluate functions. I mean, this is all very familiar stuff. We, of course, never thought of it that way at all. Okay, so these are the starting points for some conversations. I want to start with R1. This is just for the purpose of setting up a point of view. Roughly speaking, I'm going to give you a motivation for the fundamental theorem of calculus. And I know you all already know that, right? You've seen the fundamental theorem of calculus before. You might even have seen a proof of the fundamental theorem of calculus. You certainly know how to use the fundamental theorem of calculus, right? That's not my goal here. My goal here is to take a very specific point of view on the fundamental theorem of calculus, because that's the point of view that I'm going to be able to generalize in these higher dimensional settings. So again, the purpose here is to lay some groundwork. It's not to bore you with a consideration of something you already know. Alrighty, so here's where we are. Here's our Calc 1 diagram. And let's suppose, just for the sake of conversation, that we're given some interval. Now, of course, an interval is in column 1, one-dimensional thing. And suppose I'm given some function in column 0, by which I mean this is a function that I want to think of as something that I plug points into. Right? This function over here is not something I want to think of as something I do integrals of. That would be a function. So we're in column 0 with this function. This is the kind of function that I do this to. All right. So with those having been given, right? What can we do? Well, the only thing I can do, I could, for lack of any other way to spend my time on this diagram, I could take the boundary of that interval. That gives me a couple of points. Don't forget, now we have these conventions about orientation. When you take the boundary of an interval, it's not just 2 points, it's 2 points with conventional orientation. So the starting point, by convention, is to be thought of as negatively oriented. The ending point is to be thought of as positively oriented. It's just an arbitrary, weird-seeming choice. Now, having taken that boundary, I have enough pieces to kind of cook up this little recipe here. I can take this function, I can take these oriented points, and I can evaluate as such. In other words, I can take these points and plug them in to that function. and out comes a value. And of course that value is f of b minus f of a. Y'all see where this is going probably. Right? You recognize that expression? Okay, but I want to point out that this is something that we come to by reasonably natural methods. You give me some function here, some interval there. The process of taking a boundary and then plugging into our conventions gives rise to this expression on its own. Okay. All right, now what do we want to do with this? Our goal is to say, well, look, over here on this side, I'm just a little short. If I had something here, if I had some function, then I could evaluate the right side as well. And wouldn't it be cute if there were some function here that when I do this evaluation in column 1, the answer I get would be the same as this evaluation I just did in column 0. Wouldn't that be an eyebrow raiser? So that's the question we're going to ask. We're going to ask, is there something that I can put here that will make this evaluation equal to whatever that ends up being. Let's just see if we can do it. It's a arbitrary little task that we've created for ourselves, but let's see if we can do it. Okay. So the way we're going to get to what this might be is we're going to look at this expression. We're going to try to view it as an integral, if we can. And once we see that we have an integral, fingers crossed, then we'll be able to infer what it's an integral of. All right. So let's do that. Let's take this f of b minus f of a, and can I write this as an integral? So the first observation I'll make, and I think y'all have seen this little algebraic observation before. Y'all remember telescoping series from Calc 2? This is basically, it's not an infinite series, but this is roughly telescoping in the sense that if you start writing down terms here, there's a bunch of cancellations that happen. What we have, so f of x1 minus f of x0, the next term is f of x2 minus f of x1. Right, and that cancels that. So f of x1 is the negative term in the second term. It's the negative part of the second term, you might say. The positive part of the first term, cancel, etc. Everything in between pretty much cancels, and the only terms that don't cancel are that, the very first term, you might say, and then this, the positive part of the very last term. So that's kind of interesting. This thing that we're trying to reproduce as an integral, I have now been able to write this expression as a sum of expressions that look just like it, defined on smaller intervals. Okay. All right, and that's going to get us to where we need to go. I'm going to come back. I skipped a bunch of stuff up there. I'm going to come back to it momentarily. The reason this is going to get us to where we want to go is because of that. You'll notice I can rewrite like this. I hope y'all remember sigma notation, by the way. So this is very common in Calc 2, part of Riemann sums. Right? Anyway, this sigma notation, I'm going to be using this a lot. As a heads up. Rewriting it with sigma notation. What this says is that this summation, no matter what n is, for any value of n, you always get the exact same answer. That means that this expression here is a constant, independent of n, never changes, no matter what n is. Right? It's always this. And so if it's constant and never changes as, for any value of n, then it doesn't really matter what n does. And if I arbitrarily want to let n approach infinity, it's cool. It doesn't matter. We're taking a limit of something that's never changing. It doesn't change anything. And then you look at this expression and say, wow, that really is starting to look a lot like a Riemann sum at that point. Now, it's not exactly a Riemann sum. Remember, Riemann sums follow certain rules. One of them is that what you're adding up is a product of something times the size of the piece of the domain. So in this case, we're looking at a little interval. So I need there to be a delta x over here, and there isn't as of the moment. So that's easily remedied. I'm going to divide and then subsequently multiply by delta x as perfectly legal. And now, I in fact do have a limit of a sum, something times delta x. That looks a lot like a Riemann sum. Right? In fact, notice I can rewrite this thing here. That's how much did f change between xi minus 1 and xi. That's delta f. We constantly in Calc 1 classes refer to this as delta f or delta y or something like that. So we have this Riemann sum, and now I'm going to ignore some formalities, some rigor stuff. And in a class like Math 212, I think this is the appropriate choice. But I just want to acknowledge that I'm about to cheat a little bit. And I'm going to say, well, in the limit of this summation, I can go ahead and include the limit as well on that fraction. Rewrite that like that. Certain things have to be said in order for that to be valid. And I don't want to worry about that in Math 212. So punchline, then I can rewrite this Riemann sum as an integral. The integrand, we recognize, that was lucky. Limit of delta f over delta x, that's the derivative. Got one. And lo and behold, we have fundamental theorem of calculus. Okay, which again, I know y'all already know. So my point here is not that I want you to know this result. My point is I want you to see that there's a process here where we're taking, as promised, we're taking this expression that we arrived at for lack of anything better to do, and our goal was to try to figure out if we could rewrite it as an integral, and we have. Okay. Furthermore, it's an integral of something specific. It's an integral of f prime. What this says is the integrand inside of that integral, f prime, that's what this operator should be here, f prime. So I'm going to just say the derivative operator, making this f prime. That operator going there achieves my original goal of I wanted to be able to say that, that this evaluation using the boundary and this evaluation using, well, whatever this blue operator ended up being, now we see it's the derivative. I wanted those to give me the same thing. And so the argument on the previous page shows that, in fact, you do. Okay. So said differently, taking the boundary, if we take these evaluations and conventions as given, taking the boundary is kind of complementary to taking a derivative of the function in the sense that then you get the same thing in both columns. Okay. All right. So it makes sense to call this the derivative, or to put the derivative operator in that spot on the diagram. Okay. Now, I did skip over some discussion here about boundaries. I just want to basically give you an alternative way of thinking of this. We're evaluating this function f at a bunch of different points. Each one of these expressions is kind of reminiscent of a boundary. It's just that these are evaluations that have been done on boundaries. So this, bad color choice. This is f being applied to, well, a couple of points. It's the, we have the positively oriented point B and the, negatively oriented point A. Right? And if you take these 2 points, plug them both into F, you get this expression here. Notice, by the way, that is the boundary of the interval. So really what I've got, this expression here, is we're looking at f of what is actually a boundary. It's a boundary of the interval in question. Right? The interval in question, A to B, the boundary consists of those 2 points with these orientations. It does evaluating just like that. So what we're looking at here is f applied to a bunch of boundaries. Right? Similar argument. So the question of, do these things add up to that, could be reconceived as, thinking about, just forget about the f's, let's look at the boundaries themselves. Do these individual boundaries add up to the whole boundary? F evaluated on the individual boundaries adding up to f evaluated on the whole boundary. Well, what you plug it into the function, I mean, that doesn't make any difference. We're really asking, do these boundaries add up to that boundary? And so it's said definitely, we don't have to write down the f's. Right? What's happening with the boundaries is really the point. So let's take a look at, and do I have a picture of this? I guess I don't. Let me redraw our interval here. Here's our x-axis. Here's our interval from A to B. We're chopping this up into various pieces. So that's x naught, x1, x2. This is x in minus 1, x in minus 2, etc. What we're asking is, arguably, if I look at that interval there, whose boundary is a negatively oriented point there and a positively oriented point there, and then if I add to it the boundary of this interval, which is a negatively oriented point there and a positively oriented point there, and then I add to that the boundary of this interval, which is a negatively oriented point there and a positively oriented point here. You can see the pattern, right? Et cetera, et cetera. One more just for completeness. Note for each interval, the starting point is negatively oriented. The ending point is positively oriented. Adding up the boundaries of all these little yellow subintervals, green on the left, red on the right, green on the left, red on the right. You can see the cancellation happening. The cancellation is those cancel, et cetera, et cetera, et cetera, cancellation, everything cancels except for green on the left, red on the right, the boundary of the entire interval. Right? So you can think of it as the values of the function canceling. I think it's geometrically more satisfying in a way. There's less going on, you might say. You just observe, you don't have to think of the values of the functions canceling, the boundaries are canceling. Right? It's not that there's a bunch of algebraic terms that just coincidentally cancel. The terms in the algebra that cancel because we're seeing the same points appear twice with opposite orientations. It is these points as part of the boundaries of respective pieces that are canceling. Whatever that's worth. Okay. All right. So this is what we're going to model when we're moving along here in Chapter 6. Here's our updated R1 diagram. Previously, we only had a fraction of this. We've now added the derivative operator to our diagram, and we've also now added a theorem here. It's the fun one from a calculus that says, hey, not only did I just stick this arrow on here arbitrarily, right, but I now have this kind of cool fact that if you take an interval and look at its boundary, if you take a function and look at its derivative, in other words, if you put things on here and apply operators, the left side, the right side evaluate the same. Now, this is just a point of view. This is a way to kind of organize the objects that are in play in the fundamental theory of calculus. And this little organization, this pattern that we're talking about here, this is what is going to sort of reproduce in higher dimensional contexts. Okay. All right. So, let's see it happen. We're going to move up to 2 dimensions now. By the way, what we're going to do is, we're going to take this pattern that we've noticed for the fundamental theorem of calculus, and we're going to try to do something along those lines, whatever that means, in a higher dimensional setting. So what we're about to do then is we're trying to come up with a 2-dimensional version of the fundamental theorem of calculus, which is a little bit exciting if you think about it. Right? Fundamental theorem of calculus, look at the name. Fundamental theorem of calculus. Right? So we're going to take something that is fundamental and try to come up with another version of it in a more complicated context. So this is an aggressive choice. So here we go. We're going to start with, by the way, we're going to do what our diagram tells us to do. Here's our R2 diagram. Remember, we have this R2 diagram. And the R2 diagram says in column 1, if you're looking at one-dimensional domains, we have a curve on which we're going to be interested in line integrals. So the conventions tell us. All right, so here's our curve. That starts at the point A. Here, for consistency, I should use yellow here. Starts at the point A, ends at the point B. It's not an interval. It's a curve. And can I do something kind of like the fundamental theorem of calculus? Well, first thing I'm going to do is chop this up into pieces. We recall that's always the first step whenever you're doing, this kind of thing. So ... Then here's an arbitrary piece, and then ... So let's focus our attention on this piece in there. That little arbitrary piece of the curve has a starting point and an ending point. Note I'm using a naming convention that's a deliberately rip-off of what we did in the Calc 1 context. So the right endpoint, well, the ending endpoint as opposed to the starting endpoint of that piece of curve. We're calling the ending one xi, the previous one xi minus 1. Total ripoff. The vector difference between those is what plays the role of delta x. Now, of course, this is now a vector. Right? It's not just number minus number. Delta x is not just a thickness or a width at this point. Delta x is now a vector. So that's different. Okay. All right. And I'm just going to make the observations that, again, the boundaries add up just like they did before. For really the same reasons. If you look at these boundaries, let's look at these little pieces here. Here's my first little subinterval, and the boundary of that first little subinterval consists of, well, there's a starting point and an ending point. Right, now let's look at the second subinterval. That second subinterval has a boundary consisting of a starting point, negatively oriented, and an ending point, positively oriented. And then the next little subinterval has a boundary consisting of a starting point, negatively oriented, and an ending point, positively oriented. You can see the cancellations about to happen. Boom, boom. Right? Every point along the way, in the middle, that is, not the far left, not the far right, but every point along the way is, well, it's the end point of the previous piece of curve, but it's the starting point for the next piece of curve. So no matter how you slice this curve up, when you add up the individual boundaries, you're getting mass cancellation, just like we saw in the previous theorem. Okay, so that pattern continues. These boundaries add up By the way, just for terminology's sake, I like to just, I don't know, I find this terminology appealing. I like to say these boundaries accumulate. Right, so remember how we were talking about accumulation? Accumulation is a feature of, let's say, mass, for example. If I were to take a metal rod and talk about the mass of that metal rod, right? That mass of the whole metal rod is the sum of the masses that I would get if I chopped it up into little pieces. If I took a knife or a pair of scissors or whatever, snips, and chopped that up into a bunch of little pieces, the sum of the masses of the little pieces would equal to the mass of the original rod. So mass has this feature of accumulation. Again, not everything has this feature of accumulation, right? Surface area does not. For example, if I were to, take a solid, look at its surface area, and if I were to then chop that solid up into a bunch of little pieces, well, I'm making new surface area every time I take a slice. Well, now there's a new piece of surface area, and here's another new piece of surface area. I'm making new surface area. The surface area of the individual pieces is not the same as the surface area of the original solid, right? So mass accumulates. Surface area does not accumulate. Accumulation is a peculiar feature for some object to have. So what we're observing here, anyway, this is the way I like to say it, is that while mass does accumulate, while surface area does not accumulate, boundaries do accumulate. The boundary of the thing as a whole is the sum of the boundaries of the individual pieces. I think that's a nice way to think about it. So boundaries accumulate. I'm saying that a lot. Okay. Okay, so that's we've already kind of walked through that argument there. The punchline being that, well, if the boundaries accumulate, then the value of the function on those boundaries also accumulates. Okay. And here's an argument we can then make. This says the value of the function on the boundaries accumulated. This is what we just got through agreeing to up here. That's this equation here. Just like in the fundamental theorem of calculus. Not surprisingly, I could call that delta f. That's the change in the value of this function f between two successive, stop points, boundary points along the curve. Standard notation. We've been using that notation for a long time. And now, let's think about how do I compute this delta f. Let me draw the picture again. I've got a point here, xi minus 1. I've got another point there, xi. I want to know the difference between the value of the function here and the value of the function there. What's the change in the output to the function? What's the output change? Given that this is the input change, well, the relationship between input change, the displacement vector, and output change, f at the endpoint minus f at the start point, is a derivative. Right? This is a chapter 4 observation. Input changes and output changes are related by way of the derivative. And specifically in this case, because this is a real valued function, the output change is computed from the input change by way of dot product of the gradient. All right, so old chapter 4 fact. Yeah. How we doing? Everybody on board? Well, it's all over but the shouting. That's a recognizable Riemann sum. Right? That's exactly a vector line integral of this specific vector field. Remember, we talked back in a couple sections back, we talked about how a gradient of a real valued function is a vector field. This is exactly to the character a Riemann sum representing the vector line integral of that vector field gradient f. Okay, so we're done. We have a new theorem And notice how much this looks like the fundamental theorem of calculus. I mean, at a glance, it's integral equals f of b minus f of a. I mean, if you just kind of sloppy with your way you describe it, it looks just like the fundamental theorem of calculus. But it's living, it's a two-dimensional theorem, right? This takes place in R2 over a curve that might bend and twist around in whatever way, right? Very similar looking result. Any questions so far? Okay, so you see why I wanted to go through and rederive the fundamental theorem of calculus in that particular way. It's because that's the pattern that I was going to follow here that was going to allow us to draw this brand new conclusion. So here's our theorem. By the way, we do need for this function here to be continuously differentiable. It's not the kind of thing we're going to focus on in this class. Okay, so, and now we can supplement our diagram. Let me remind you, this is what our R2 diagram had previously looked like, and what we've added to it now, the gradient operator. The gradient operator is what makes this fundamental theorem of line integrals, we call it, actually work. That's the operator which, if you were to take a curve, look at the boundary points, evaluate. In other words, if you were to look at the f of b minus f of a that we just got through talking about, then this operator, gradient, that's the operator that gives you the vector field that when you evaluate it in the right column, gives you the same thing as the left column. Yeah? Everybody on board? Okay, I'll show you an example. Suppose we want to compute this line integral. Now, side note, I know you all know how to compute line integrals, right? But you know a method for how to compute line integrals. You know the brute force way to compute line integrals. This is in many situations, much better, much more powerful way to compute line integrals. There is an asterisk here. This doesn't always apply. You can't just forget the old method for using line integrals. We need that old method for using line integrals also. But in some situations, this is totally awesome. So here we go. Curve, orientation, vector field. I can ask what's the value of the line integral. We've got a curve, oriented curve. We have a vector field, and y'all could, chapter 5, plug and chug on this. But you can kind of see how the calculation is going to go. I mean, you have a circle. When you parameterize a circle, you're going to either have trig involved or square roots if you make a bad choice, right? One or the other. Either way, you're going to end up with integrals that have trig in them. And it's like, it's not the worst thing in the world, I suppose, but it's you're going to have to write some stuff down for sure. Here's the alternative. Notice that this vector field is a gradient. It's a gradient of this function. We're not just looking for a random line integral of some random vector field. We're looking for a line integral of a very special vector field. A vector field that is a gradient of something. We have a theorem about that. If you want to compute a line integral of a gradient, there's your magic formula. Just plug in f of b minus f of a. No integrals. Right? No single variable calculus integrals. Anyway. So that's what we're going to do here. We have our function to plug into. There's our fundamental theorem of line integrals. Now you got to think through what the boundary is. We have a curve here. It was the upper semicircle. Let's see, upper unit semicircle, counterclockwise. That means that we're starting there. We're ending there. So f of the ending point minus f of the starting point. Right, that's the formula. And easy function, 2x plus 3y, plugging in easy numbers, it's just ones and zeros. And boop, we're done. Didn't have to do any trig. Didn't have to remember derivative and antiderivative formulas. It's almost too good to be true. Everybody see what happened there? Okay. All right, it's a pretty cool theorem. That said, I do want to point out that there's an asterisk. This theorem is not going to magically allow you to compute all possible vector line integrals. This will only allow you to compute, and you can see it right here in the statement of the theorem, this will only allow you to compute vector line integrals of gradients. So the vector field in question has to actually be a gradient of something. If your vector field is not a gradient of something, then what does this have to do with it, right? This specifically says line integral of a gradient. If your vector field isn't a gradient, oh well. And then you got to go back to chapter 5 and brute force. Plug and check. Okay. Now, so you might think to yourself, well, why wouldn't a vector field be a gradient? Isn't this kind of can't you always find such a thing? Think back to Calc 1. In Calc 1, the analogous idea was antiderivatives. Right? A function whose derivative was a given thing. Here we're just looking for a function whose gradient is a given thing. So since I could practically, except for a few weirdo cases, I could practically always find antiderivatives, shouldn't I practically always be able to find antigradients? Well, I can call them antigradient. Is this function here, the f function, I would call it antigradient. Sadly, it's just not true. The analogy is not analogous. The analogy does not extend. There are lots and lots of easy, simple vector fields that do not have an antigradient. And it's not that we don't have the notational ability to represent it or that we haven't figured out how to find it yet. There is no antigradient. It is easily observable that there is no antigradient. And we'll talk about why that is in a few minutes. Okay, so got to be careful with that. Don't just assume you can always find the elusive antigradient. Okay, by the way, there's a three-dimensional version. Looks just exactly the same in R3. By the way, if you go back through the argument that we made here, you notice that nothing about this argument is peculiar to R2. How do we relate input changes to output changes in R2 versus R3? Same formula, dot product of the gradient. Everything, the argument is identical. And I just like to present them as separate theorems because we're going to draw them in separate places. But here's our R3 fundamental theorem of line integrals. And then here's what our R3 diagram now has been supplemented into. We're going to add the gradient operator there, and thus giving us our fundamental theorem of line integrals in R3. Said differently, studying this boundary operator between curves and points motivates putting this gradient operator between functions and vector fields to make a theorem that lays on the page in the same way that the fundamental theorem of calculus lays on the page. Okay, here's an application. It's morally equivalent to the one we just did. Just notice that this is now an R3 an R3 situation. We have a three-dimensional vector field. We have a curve in R3. Notice this curve's in R3 because there are visibly 1, 2, 3 components on that curve. Right. But the solution is the same. We notice that vector field, missed. That vector field is a gradient for a particular function, and therefore we can do the fundamental theorem of line integrals. Okay, how to find these antigradients. Right, finding the antigradient is the thing. That's what allows you to use the theorem. If you have some line integral you're interested in, and if you would like to use this formula, this is the thing that you got to figure out, right? What is that anti-gradient into which I plug, and do f of b minus f of a. Okay, so what's the anti-gradient? So here's the process by which we're going to find it. Remember, this is what a gradient is. A gradient is a vector of partial derivatives. Chapter 4, old news. Okay. If we have a vector field, as usual, let's call the components P, Q, and R. We have a vector field here, PQR, and I want to know if it is a gradient. What I want to know is there some function little f that makes these vectors equal? Is there some function little f where all three of these equations are true? And notice that these three equations here I can pull out, look at separately like this. I just need for P to be the x partial of f. I need for Q to be the y partial of f, and I need for R be the z partial of f, right? I have three needs. If I can find a function little f that makes all three of these equations happy, then we are good, right? That little function little f is our anti-gradient. So this is our puzzle. Let me observe that those equations are the same as these equations, really. This is kind of backwards. These morally say the same thing. I mean, if P is the x partial of f, then f is the x anti-partial of P. Okay. Y'all remember derivatives and antiderivatives? Stuff from top one. Now, don't forget your plus C, right? Now we have to be careful. Plus C, why did we have to put plus C when we were talking about antiderivatives back in Calc 1? We had to put the plus C because, well, when I take the x partial of both sides of this equation to get what I really care about, that that this equation works, when I take the x partial, if I had a constant somewhere in this equation, the derivative of the constant would be 0, and it wouldn't affect the satisfaction of this equation. So, plus C. Okay, sure, but now, really, what I need to say is plus anything whose x partial would give me 0. Anything that, by the process of taking an x partial, would not affect the satisfaction of this equation. Well, what is it that when you take an x partial, you'll necessarily get 0? And it's any function that doesn't have x's in it. Right? So this is a little bit weird. This is no longer really a constant. You can call it a partial constant. In the same sense that this is a partial derivative and that's a partial antiderivative, this is a partial constant. It's a constant, at least in the sense of derivatives with respect to x. So, and then likewise for these others over here, this is just something whose partial with respect to y is 0, so it's a partial constant with respect to y, or it's any function of x and z. Okay, so here's our game then. What we need to do is we need to find some function. I need to find some function that's simultaneously equal to these three different expressions. And the only thing is I don't know what these expressions are exactly. I can compute that anti-partial, but I don't know what this C1 of y and z is, and C2 of x and z. I don't know. It can be anything as long as it's only x's and z's, etc. So we have a kind of a game going forward. The game is, once I compute these three anti-partials, can I think of functions, three separate functions, partial constant functions, to put in there that make these things all equal to each other? And the answer to that question is sometimes, not always. And it's pretty easy to see the cases where very clearly it's just not always going to work. So here's an example. Suppose I want to find the anti-gradient for this vector field. Notice that this vector field has three components. So there's my P, Q, and R. Here's the game. I need for P anti-partial with respect to x, Q anti-partial with respect to y, R antipartial with respect to Z, I need those all equal to the same function, this elusive antigradient that I'm looking for. With the understanding that, you know, I'm allowed to add in these constant functions like that. And so here's how that game fleshes out. The antipartials are easy to write down. Here they are, and those are the antipartials that I, you know, sort of most naturally write down. And so I need to start playing the game. What function of y and z can I put in there? What function of x and z can I put in the other place? And can I make this all fit? So the way you play this game is, it's not a deep game. What am I going to have this be? If I need for these two things to equal to each other, well, it kind of has to be that, right? There's no 2yz up here. There is a 2yz down here. If I want these things to equal, I need there to be a 2yz on this first line, and not over here, and it's not there, so it's kind of got to be there. You know, so that kind of a thing. And not hard to persuade yourself that, yeah, you can totally do this. Here's the answer. That's the function that does it. 2yz is what makes that one work out. xz cubed is what makes that one work out. See, it had to be there because it was there and there. Yes, you know, again, it's not deep strategy. It's not, I mean, I'm no good at Sudoku, but I can do this, right? X squared y is kind of what that has to be because, well, where else is it going to be? So this satisfies all those equations, and therefore it is the antigradient we're looking for. Okay, so that's the game, and I claim that you will not always be able to win this game. Let me give you an example of a game that you cannot win. Easy to write down. Let's consider this vector field, which is negative y comma x. That's not a scary looking vector field. Here's the game that we would have to win. I would need to find some function that on the one hand it's going to have to be the x antipartial of negative y, you know, plus possibly some function of y. I would also need for it to equal to the y antipartial of the second component x, plus possibly some function of x. And if you think about it, what that means is I need negative xy plus c1 of y, positive xy plus some function of x, and we lose, right? Win this game for me. You can't. I mean, there's nothing you can do. It's pretty easy to persuade yourself. Okay, so not every vector field has an antigradient. Easy example there of a vector field that, and I emphasize, this is not some business about, oh, you have to use infinite series, or, you know, some clever notation that hasn't been invented yet to come up with the antigradient. Absolutely not. It doesn't exist. There is no antigradient. Right? So I don't care how clever you get, you're not going to find an antigradient of that function. Okay, so that's one of the disappointments about the fundamental theorem of line integrals. I mean, the fundamental theorem of calculus, every continuous function has an antiderivative. I mean, it might be hard to write it down, or maybe I can't figure out how to find it, or something like that. But it exists. You give me a continuous function, there is an antiderivative. So the fundamental theorem of calculus applies extremely broadly. The fundamental theorem of line integrals, sometimes it does, sometimes it doesn't. Right? So, it's a disappointment. Okay, moving along. All right. So we're going to do it again. Let me remind you. We had a fundamental theorem of calculus. We took a certain point of view on this diagram of, you have an interval, you look at the boundary, you evaluate, kind of find an operator, right? So there was this point of view we had on how to think about the fundamental theorem of calculus. We used that as a template and came up with a kind of a vector line integral equivalent result. So sort of a fundamental theorem of calculus for line integrals. What we're going to do here is dimensionally weirder. Definitely dimensionally weirder. The thing about the fundamental theorem of line integrals is, okay, sure, it takes place in R2 or R3, but it was still a one-dimensional curve as opposed to a one-dimensional interval. I mean, it was still, in some sense, it kind of was still a one-dimensional thing with zero-dimensional boundary points. It was pretty analogous. We're going to now try to do the same thing to a totally different situation. Not to a one-dimensional curve in two-space, but to a two-dimensional solid. Two-dimensional solid, right? With a one-dimensional boundary curve, and can I come up with something that's kind of like the fundamental theorem of calculus? That fits, that follows the pattern on the diagram like the fundamental theorem of calculus. That's going to be our goal. So chapter 6 is weird. Right? So this is our first example. So, hold on. But notice that I'm going to follow the same pattern. Here's the part of the R2 diagram that I want to focus on. Notice I'm going to have a domain. Now that's a two-dimensional domain here. To which I'm going to take the boundary. And then I'm going to say, oh, well, now I have a vector field and I have a boundary curve, and I can take line integrals of that vector field on that boundary curve, and I'm going to get some expression, and I'm going to ask the question, is there some operator that I can apply there such that a double integral will give me the same thing? So we're going to be aiming for that same pattern. Whatever we end up with, we're going to declare as being at least in terms of the pattern, kind of like the fundamental theorem of calculus. So can we do this, and how does it work? What do you end up with? So now we have to start off with boundaries. By the way, notice here we have here's our two-dimensional region here, and it has a one-dimensional boundary curve. Remember we talked about the conventions on boundaries and the conveniently simple solid that I've drawn here. The boundary goes counterclockwise around that region, around this curve. So, do boundaries accumulate? Right, that was the thing that made it all come together, the thing that allowed me to write these equations. Where am I? Yeah. The thing that allowed me to write this down, our very first step in the fundamental theorem of line integrals, was the fact that the boundary of the whole curve was indeed a sum of the boundaries of the individual pieces. So I needed boundary accumulation for step one to even get started in the conversation. So do we still have boundary accumulation? Well, in this new context, it's a pretty different picture. Here's my first example of what boundary accumulation would kind of look like. There's a rectangle. There's the boundary of that rectangle. Right? What I want to know is that boundary equal to the sum of the boundaries that you get when you chop the rectangle up into little pieces. So is that equal to the sum of that boundary plus that boundary? It's not obvious. In fact, it kind of looks like it isn't. I mean, notice that this edge. Oh, whoops! This edge here is showing up, and I mean, if you start thinking about, well, just look at the points. Think of these boundaries as like you've got a plot of land, and you're going to talk about a fence that you're going to build around it. building a fence around the whole thing is less fence than if you have to build a fence around that and a fence around that, right? Because you have to build two separate pieces of fence along in there, and it doesn't seem like it's going to work out. But it does. It works out perfectly. So you can write this down a couple of different ways. You can write it down algebraically, but I think an easier way to see it is like this. If I take this rectangle, I'm going to represent its boundary. Now keep in mind the boundary comes with orientations. I'm going to represent those four pieces of boundary by these arrows representing both which edge and which orientation. So the boundary of D1 is those four edges. I should say those four oriented edges. Right? The boundary of D2 is these four edges, following the rules, right? Always go, I'm going to say counterclockwise, but always go such that the solid is on your left. Okay. So I've got four purple edges, four red edges, and how do those add up? Well, beautifully. These two edges right here, that's the same edge twice, but with opposite orientations. And so they cancel. When you cancel those two edges, I mean, they're the same edge, just with opposite orientations. So the negatives of each other. And check it out, that is indeed the boundary of the union. Isn't that crazy? But it's counterintuitive. You got to think it through. The orientations are the key. I mean, the conventions that we've made about, when you take a boundary of an oriented thing, what are the induced boundaries on the little pieces? Actually, what are the induced orientations on the boundary pieces? Those conventions, in this case, always counterclockwise, are what make this edge show up twice but with opposite orientations and therefore cancel and thus give us the result. And it's geometrically very different from what we saw in the single variable case, but it's also pretty darn analogous. Let me go back here it was. Here was the cancellation that we saw happening. We were looking at the fundamental line integrals, and this point, this piece of boundary appears twice and with opposite orientations because of our conventions about boundaries. So something appearing twice but with opposite orientation and then canceling. That's, like I say, it's geometrically different because this is a different context. But that pattern of it appears twice with opposite orientations and canceling is exactly what we just saw happen here. Exactly what we just saw happen here. So, it kind of works. I claim that same sort of thing is going to work no matter how many pieces you have. So if you have some great big monstrosity of a region, some solid, let's say like that, right, if you slice that up into a bunch of different pieces and ask, well, what happens when you look at on each individual piece? When you look at the various different, here's, you've got that edge, and you've got that edge, and you've got that edge, and you've got that edge. Yeah, that's true. But you've also got those, and those, and those, and those, and those. I did that one. And those, and those. Anyway, there's all of them in consideration at the same time. And so notice that each edge, each edge here, that's on the inside, each what you might say new edge that we're concerned about the fact that we created because we just sliced in there and appears twice. Part has the boundary of the one side, part has the boundary of the other side, always with opposite orientations. It cancels in a puff of smoke. And the only things that don't cancel The only things that don't cancel are the ones that are actually on the boundary of the union. So boundaries accumulate. Let's see, where did I write that? Have it on here. Yeah. So the boundaries accumulate again. So look, you just got to spend a little bit of time, thinking through. I think this is a good picture to think through, right? Because this is the easiest one, and you can really focus on what's really going on this edge. Why don't we get two of those edges? I feel like there's two of those edges. Why is it 0, not 2? So think about that. It's because of the orientations, right? Think about this, larger value of n picture, and that gives us our result. So here's our starting point. So the boundary of the whole thing is the sum of the boundaries of the individual pieces that you get when you slice up the whole thing, right? So we have this two-dimensional region. The boundary of the entire thing is the sum of the boundaries of each of the individual pieces. That's where all the cancellation happens. So these are the same, what I have in green over here, what I have in green there, they're the exact same domains. And so line integral over them, same domains, same line integral, right? And so what we have then is that the line integral, the boundary line integral around the original solid, is the sum of the boundary line integrals around the individual pieces. Right? This is true no matter what n is. It's always equal to the same thing, so therefore this is a constant. If something's constant, it doesn't matter. If you take a limit as n goes to infinity, it makes no difference. As n goes to infinity, nothing changes anyway. So I get this expression. My gosh, that's starting to look vaguely like a double integral. Not exactly. Right? And if this is going to be a double integral, I need to have a delta A over here, right? So a double integral is a summation, something times area. So I've got to play the same little trick that I did back in the earlier, and that is to divide and then multiply by delta A. It's legal. It's a little kind of a hack, right? But note that gives me what I want. Then now I very literally have a sum of a function times area. This is a double integral. It's a no kidding double integral. And double integral of what, we ask. So this is the awkward point. We've got this thing in here, and the line integral, the boundary line integral that we started with, is equal to a double integral, and that's nice and all, but we don't know what this expression is on the inside. When we were at this stage in looking at the fundamental theorem of calculus, the thing that we had here was limit of delta f over delta x, and we're like, oh, hey, there's our old friend. There's a derivative. What are the odds? Convenient. And I just said, oh, derivative, just, wrote it down. That was lucky. It was a lucky break. It was not a necessary break. That was just good fortune. Okay. Well, what we have here is a situation where I don't happen to recognize this, but that doesn't mean this isn't something that can be computed. And it turns out that this is. You can totally compute this. I don't want to focus on that in Math 212. It's details. So I don't want to bother with this. I'm just going to assert what this is. I claim that can be computed by that formula. It's dq dx minus dp dy. And if you're curious, if you want to see why that is, come talk to me in office hours. I'll be happy to show you. It's not that big a deal. That's what it is. Okay. And I'm not going to hold y'all responsible for why this is. Why does this integrand turn into that? that's you're absolved. So, point is, it's something that can be computed. There's the formula, and so here's our theorem. And this, I claim, is kind of like the fundamental theorem of calculus in a way. We started looking at an expression on the left. We asked, can I write this as a double integral? Answer, yeah, here it is. There's a double integral, and this is the operator that fits in that spot. It's what we call Green's operator, and this is called Green's theorem. Okay, so here's the, by the way, this is the notation I like to use for Green's operator. I think I may have made this up. I'm not sure. I don't remember if I saw this somewhere else or if I just decided that they should have a name for this operator. I'm tired of writing out the whole thing. And so anyway, in the purposes of this book, I'm going to write GRN, shorthand for Green. But it's just a shorthand for that expression. So with that in mind, here's our theorem. Green's theorem. It's exactly what we wrote before. Note the alternative notation here for Green's operator. And here's our new R2 diagram. You know, we previously had some of this stuff here. We now have this Green's operator to go in that spot. And we now have a boundary theorem. And notice that this boundary theorem fits the exact form of the couple of other theorems that we've already seen. This fits the form of the fundamental theorem of calculus. It fits the form of the fundamental theorem of line integrals, 2 and 3 dimensional. And it's specifically what I mean is if you take a domain. Now, this is a 2-dimensional domain sitting inside of R2. Right? But if you take a 2-dimensional region here, if you look at the boundary of it, and if you have some vector field, and if you do the evaluation on the left side, namely if you take a vector line integral, because that's what we do in Chapter 6, when you have a vector field and a curve. Vector line integral of that vector field around that curve. If you were to, on the other hand, apply Green's operator and do a double integral of Green's operator of the vector field on that original domain, then you get the same thing. So, cosmetically, if you look at just the theorem by itself, it does not look like the fundamental theorem of calculus because it's like, where's the f of b minus f of a? Where's the, there's a double integral in this for crying out loud. It does not look like the single variable fundamental theorem of calculus. But on the diagram, in terms of, what's relating to what, we're talking about boundaries, 2 evaluations equaling each other. This really fits the pattern that we have seen. This is our 4th version now of theorems fitting the same pattern. Okay. All right, so I'm going to show you some examples. Couple of quick comments before we go on. Just FYIs as we proceed here. The fundamental theorem of line integrals was sort of over here, right? It relates line integrals to functions, and overwhelmingly often we want to go that way. Overwhelmingly often, if you have a line integral that you want to compute with, conveniently evaluated by plugging in a certain way to a special function. It's pretty rare that we want to evaluate a function by realizing it as a line integral, right? That's just, this doesn't really come up very often. But weirdly, that pattern does not really hold here. It's usually the case not that we go this way. That's usually not what you do. It's usually not that you have a double integral and you very proudly say, hey, alternatively, I can compute it with this line integral. It's just not. There is a case, and I'll show you one. But most of the time it goes the other direction. Most of the time it's, I've got a line integral, and I would like to avoid whatever ugliness is in this line integral by alternatively rewriting as a double integral. That's just how it tends to get used most of the time. So that's the first thing I wanted to comment on. The other thing is, I wanted to point out that there is again an asterisk. Right? If you're here, there is this question of, can you find an anti-gradient? Right? If you're trying to turn a line integral into just, plugging into some function, that's your goal. The worrisome problem is, can I find the anti-gradient? And the answer is maybe not. You might not be able to. Not everything is a gradient. Therefore, not everything has an anti-gradient. There is an analogous worry when you're looking at Green's theorem. It's not a question of whether you can plug in and compute Green's operator. That's just calculus. That's just take some partial derivatives. That's no big deal. You can always do that. That's if the function's appropriately differentiable. The worry is there an anti-boundary? Right? If you're interested in some line integral, you want to compute a line integral around some curve, notice Green's theorem only answers the question if that curve is a boundary. And this is not a mere technicality. It's not technically this only, the theorem doesn't go through if there is, if it's not a boundary. No, you need the region whose boundary it is. Right? If the curve that you're interested in is not a boundary, then there is no two-dimensional region over which to do your double integral. It's a complete crash and burn. Right? So this is the big worry in this context. If you want to use Green's theorem, is there an anti-boundary? Or said differently, is our curve a boundary of something? Okay, so you always got to be on the lookout for that. If you have a line integral, if you're thinking about using Green's theorem, you have to ask, is there an anti-boundary? Okay, so let's see an example here. We're going to do a line integral. We've got a vector field there. There's the vector field. We have a curve that traces... let me use a different color. Our curve is a unit circle going counterclockwise. Okay, so reasonable question. I can ask, how do I compute the line integral? Yellow. How do I compute the line integral? Let me remind you. You want to brute force this, I guess you could. But that's going to be annoying. I mean, look what we've got here. We've got not only an exponential, but we've got arc tangent in here. That's no fun. But worse, our curve traces out the unit circle. That means that when we parameterize our curve, if we are going to brute force this, we parameterize our curve, x and y are going to be trig functions. So this is not just e to the x. This is e to the power of a trig function. That's annoying, right? We're going to have arctangent of a trig function, which, again, if you remember your trig, you can play that game. But it's, right? So this is not going to be an easy problem in terms of the calculus if you decide, I'm just going to brute force it. Okay, so let's apply Green's theorem. The first big question, is our curve a boundary? You got to draw a picture. Our curve traces out the unit circle going counterclockwise. There's our curve. And you just have to make a geometric appeal. Look at that curve, unit circle going counterclockwise. Is that a boundary of something? And yeah, it is, right? I mean, that curve is a boundary. It's a boundary of this disk. And the good news is that if a curve is a boundary, it's usually pretty straightforward to see what it's the boundary of, right? Look at it. Does our curve put a fence around something? If so, what did it put a fence around? Right? It's usually a pretty straightforward observation. But nevertheless, it's got to be noted there has to be an anti-boundary in order to actually proceed here. Okay, so all right, so here we go. Green's theorem says that because we're looking at a line integral specifically around a boundary curve, I can rewrite the line integral with the double integral of Green's operator. It's just straight up Green's theorem. Green's operator. You take this vector field, plug it into Green's operator. Remember, this formula is dq dx minus dp dy, so we're going to take the x partial of that second component. We're going to subtract the y partial of the first component. And a lot of good fortune happens. This great big thing, Green's operator, ends up just being 2. You won't always get that lucky. I arranged for this to work out awesome, right? I'm making a pitch here, so that worked out really nicely. But anyway, it's like I say, you won't always get that lucky, but we got awful lucky here. What would have been a nasty integral turned out to be a barnyard variety. What's the area of a disk, right? And so easy answer to the question. I didn't have to do any weird integrals of arctangent of sine t or e to the power of cosine t, anything weird like that. Straightforward calculation. Okay. All right, that's it for today. I do have homeworks to. No, I don't have any homeworks to return, but I do need to take attendance for those who came in a couple.